So, now we do have another example where we do have the CC followed by CE amplifier, and what we have here, it is the CC stage, it is directly getting coupled to CE stage, and you can see here the in this CC stage, basically this part is the CC stage, and normally we do have a current sink here for proper biasing, but here we assume that whatever the emitter current we do have out of Q 1, that is entirely getting consumed to the base terminal of Q 2. So, hence we may assume that this bias circuit is not required. On the other hand, for Q 2, which is forming the CE amplifier. So, we do have CE amplifier here, and for this CE amplifier, while we are feeding the signal at the base. So, along with the signal, we also require meaningful DC voltage at the base of Q 2. Now, again here we assume that DC voltage of Q 1, it is sufficient to feed the signal at the base of Q 2, or you may say that whatever the emitter current we do have out of Q 1, that is good enough to make a bias of the Q 2. So, in summary, what I like to say that Q 1 is biased by base terminal of Q 2. So, it is biased at its emitter by the base terminal of Q 2. On the other hand, Q 2 is biased at its base terminal by emitter current of Q 1. So, they are, I should say, they are helping each other to have mutual bias, and hence we can simplify the biasing arrangement. So, that is what we do have very simple bias here. Now, here for comparison with our previous circuits, we are setting the value of this R 1 such that the current flowing through this Q 2, we are expecting that it will be say 1 milliampere. So, if the IC of transistor 2 it is 1 milliampere, and then we like to retain the same DC voltage at its emitter. So, we are maintaining RE 1.2 K, and then the required current here, since its beta it is 100. So, the required current here it is close to 10 microampere. And if I say that this 10 microampere current of transistor Q 2, base current of transistor Q 2, it is equal to the emitter current of Q 1, then again, because the beta of Q 1 is also 100, the required base current for Q 1, it is I should say 10 microampere divided by 100. So, that is in the order of sub microampere. In fact, so this is equal to 0.1 microampere. So, the required resistance here, it need to be very high, and I just made some calculation, and it is observed that if R 1 it is say 98 mega ohm, then we are getting this current is 1 milliampere. So, I will show you the simple calculation to get this the emitter current of Q 2 is equal to 1 milliampere. So, if I start from say 12 volt here, and then we do have 2 VBE drop here, and if I assume that these 2 VBE drops are approximately equal to 0.6, then the remaining drops, namely 10.4 volt, it is across RE, this across RE and R1. So, I should say that 12 volt minus 1.2 volt due to the 2 VBE equals to IB1 multiplied by R1 plus IB1 multiplied by 1 plus beta 1. So, that gives the base current of Q2, and then if I multiply with 1 plus beta 2. So, that gives us the emitter current here. So, that multiplied by RE is the drop across this RE. So, here we know beta, we know R1 and then RE, and from that we can find what will be the IB. So, this IB1 it becomes, so this is 10.8 volt divided by R1 plus RE multiplied by 1 plus beta 1 multiplied by 1 plus beta 2. So, if we put the value of these resistors, then what we are getting it is so 10.8 divided by we do have 98 mega ohm, and then 1 plus beta 1 is 101 multiplied by 101 multiplied by RE, it is 1.2 kilo ohm. In fact, that gives us close to 0.1. To be more precise, in my calculation it came 0.097 microampere, and from that we can get E1 equals to. So, if I multiply this by 101, we do get 9.8, maybe 9.85 microampere, and that gives us the base current IB2, which is IE1 equals to 9.8 microampere, 85 in fact, to be more precise, and then we are getting RE1, sorry RE2, which is 1 plus beta, that is 100 multiplied by 9.8 microampere. So, that gives us 1 milliampere. So, now we have the collector current. So, we can say that IC1 it is approximately equal to same as this IE. So, that is 9.8 microampere, and then we also have IC2. We can approximate that this is by 1 milliampere, and from that we do get R pi 1 and then R pi 2. R pi 2 it is 2.6 kilo ohm. Earlier we have done this calculation, and on the other hand R pi 1 and its current is quite low. So, in my calculation it was around 265 kilo. Yeah, I think around that. So, if I am having these two resistances are known, then we can find what will be the input resistance of this circuit. So, what is the input resistance. That is what it is very important for this circuit, this configuration, because we like to increase the input resistance by putting this CC stage. So, the input resistance here R in, it is parallel connection of R 1 and whatever the resistance we do have. So, let me use this space here, R in equals to R 1 coming in parallel with whatever the resistance we do have, and what we have the resistance here, it is R pi 1 coming in series with 1 plus beta 1 times R pi 2. So, we are ignoring this R naught here, we consider only this R pi 2, and that gives us roughly. So, we can say that this is 100 and 101 and 2.6 kilo ohms, it is getting multiplied by that factor, and then we do have 265. So, roughly you can see that this is 530, around 530 kilo ohm in parallel with R 1, which is 98 mega ohm. Okay. So, then you may approximate that this is by 530 kilo ohm. So, if I am having only this C stage, the input resistance here it was only 2.6 K, but if I am putting the CC stage in front of that, the corresponding input resistance it is getting increased. So, that is why for op amp whenever we like to increase the input resistance, we put the CC stage in front of differential pair. Whenever we will be talking about differential amplifier, we will discuss it further, and instead of using this CC stage, in fact people use something called Darlington pair. So, we will see that, but before that let me see the input capacitance of this circuit. So, let me clear again to make the space. So, C in of this circuit, it is we do have C mu of transistor 1. So, we do have C mu of transistor 1, and this node it is AC ground. On the other hand, this C pi it is bridging the input base terminal and emitter terminal of Q 1, and its gain it is very close to 1. So, we may say that effect of this C pi it is negligible. So, this is helping us to reduce this this input capacitance, and you may recall that if you ignore say CC stage, and if you are directly considering this is the primary input, then the input capacitance at this node it was mu C mu 2 multiplied by its gain, the voltage gain, and the voltage gain here it is, we know it is quite high, and then also the C pi 2. So, in fact, this is dominating the AV and C mu. So, C mu 2 multiplied by G m into R C, that is what primarily we do get, the gain plus 1. So, definitely if you compare this value and this value, this is much smaller. So, again putting this CC stage, it is helping us to reduce the input capacitance and to increase the input resistance. That may be useful in case if you are feeding the signal from a signal source having very high source resistance R s. compared to CCC amplifier, there is another configuration, something called Darlington pair, and we will see that what is the difference, basic difference. In fact, their configuration wise they are very close, but there is a small difference. In the next slide, we will be discussing about that. So, here we do have this Darlington pair. So, you can think of this is one transistor, its base terminal is here, and then its collector is here, and then emitter it is here. And then if you put this structure or you can say composite pair in C configuration, what we can get it is we will be getting the same gain of CE amplifier, namely GM into RC, but the main advantage here it is the input resistance here it will be quite high. And for our comparison with the previous circuit, where the collector of Q1 it was connected to supply voltage VCC. On the other hand, here in the Darlington pair, collector of the first transistor it is connected to collector of the second transistor. In fact, both the collectors are connected together. Now, DC operating point wise, both this circuit and this circuit are I should say very close to each other. That is because whatever the collector current we are drawing here, which may be flowing through RC now, unlike the previous case, where the collector current of Q1 it was directly coming from VCC, but since this current is very small compared to the collector current of Q2. So, we can say that all practical purposes the operating point of this circuit and this circuit they are same. But the main difference here it is in the previous circuit C mu of transistor 1, the other end of C mu it was connected to the supply voltage which is AC ground. As a result, the input capacitance here it was only C mu, and that is as is. Whereas, for this case the C mu here it is connecting the input terminal to the primary output of the circuit, and we know that from this primary input to this primary output we do have very good gain. So, the consequence is that the C mu of this Q1 it is getting multiplied by Miller's factor, and that produces big amount of input capacitance. So, the C in it is C mu 1 multiplied by 1 plus GM into whatever RC. So, I should say that this circuit is definitely better in case if you are looking for an application where input capacitance is very important. Otherwise, the other performance matrices they are identical. So, maybe you can calculate the corresponding gain and all offline, but so far whatever the things we like to discuss, namely the main purpose of using CC stage to enhance the performance of CE amplifier, that is done. So, in summary what we have covered so far, it is that we have talked about the usefulness of common collector and common drain stage through numerical examples, and those examples are primarily CE followed by CC, CS followed by CD. So, these two it was covered before, and just now what we covered it is common collector followed by CE stage. Rather, this CE stage it is the main amplifier which is preceded by the common collector stage, or equivalently you can say that Darlington pair we can put in amplifier configuration, and then there we have seen that input resistance it is getting enhanced. This is helping not only input resistance got increased, but the input capacitance also got decreased. I think that is all I would like to share. Thank you for listening.